So you've probably heard of the Monty Hall problem. It's pretty popular, and for good reason. It's got an interesting history and a kind of paradoxical answer. And if you haven't heard it, don't worry, I'm going to explain it in this video. But because it's so popular, what I really want to do is get beyond it. Tweak a couple assumptions and see how that changes the problem. And ask a couple more questions that I find equally interesting and similarly paradoxical, but are perhaps a little bit less well known. Anyways, for anyone who hasn't heard it, here's the Monty Hall problem. It all centers around a hypothetical game show, loosely based on the old show Let's Make a Deal. Apparently this show was hosted by Monty Hall, hence the name of the problem. So here's our host trying to explain the rules. Fortunately, the rules are really simple. There's a contestant, apparently a contestant who's really excited to be there, who will win the prize that's behind whichever door she selects. Behind two of the doors are goats, a prize that presumably nobody really wants. But behind the third door is a brand new car. And while the host knows which door the new car is behind, the contestant has no idea and no way to figure it out until the doors are opened. So the host asks the contestant to pick a door, she walks over in front of it, but before she opens the door, the host decides to add a little bit of drama. He knows which door the new car is hiding behind. So he opens a door that the contestant is not in front of that has a goat behind it. A hush falls over the crowd. They probably break for a commercial at this point. But eventually he asks the contestant if she would like to stay with the door that she originally picked or change to the other door that is not yet opened. And what the Monty Hall question asks is, now that a goat has been revealed behind one of the doors, does it make sense statistically speaking to change doors? Most people say, nah, it doesn't matter. There's two doors that are still closed. The car's behind one of them. The host hasn't given us any information about either of these two doors. Don't bother changing, save your energy, it's 50-50. If that's what you were thinking or you're convinced by that argument, you're certainly not alone. This problem really became famous when a different solution was published in a magazine. The author, Marilyn Vos Savant, who wrote a weekly column in Parade magazine, and was something of a celebrity herself, appearing in the Guinness Book of World Records as the person holding the highest IQ.
That it's 230 is her IQ score.
Wow.
That's the highest ever recorded. Please welcome Marilyn Vos Savant, ladies and gentlemen. Hi, Marilyn, how are you? Hi, nice to see you.
Anyways, she claimed if you're the contestant, you should always switch doors, and that doing so doubles your chances of winning the car. Essentially, when the host opens a door, it doesn't give you any information about the door you're standing in front of, but it does tell you if you are standing in front of a goat door, which of the remaining two doors the car is behind. Initially, the probability that the car is behind each of the doors is 1/3, but when the host opens a door and reveals a goat, that 1/3 probability, informally speaking, transfers to whichever door you're not standing in front of. And maybe you're like, wait, what? That makes no sense. Why would probabilities transfer? What does that even mean? Well, if it was obvious, it wouldn't be a paradox, right? You wouldn't be watching a video on it in the first place. In fact, the solution is so counterintuitive that Marilyn claims she received roughly 10,000 different letters from readers telling her she was wrong. Roughly 1,000 of these letters came from doctoral mathematicians, and supposedly even Paul Erdos, a famous mathematician and super interesting guy, thought that Marilyn was wrong. But fortunately, there's a way to explain it. There's actually lots of different ways to explain it, but one in particular makes a lot of sense to me. Pretend there's two different people. Sarah, who always stays at the same door she originally picked, and Carla, who always changes doors when the host gives her the option. And pretend both Sarah and Carla are lucky enough to be on this game show 30 times. So each of them has 30 chances to win a new car. If we can figure out how many cars we'd expect each one of these ladies to win, then all we'd have to do is compare the results to see which strategy is better. For Sarah, it's fairly easy. Since she always stays at the same door, the only way she's going to win the car is if she initially lines up in front of the door that has the car. Since there's 3 doors and the car is equally likely to be behind any of the 3 doors, there's a 1 in 3 chance that she initially lines up in front of the door that has the car. She's not paying any attention at all when the host opens a door to reveal a goat because she's already decided she's not changing doors. So 30 tries, 1 in every 3, she lines up in front of the door that has the car. We'd expect her to win 10 cars. And what about Carla, who, remember, will initially pick a door at random, but after the host opens one of the 2 goat doors, she's always going to change doors? Well, if she initially picks the door that has the car behind it, she's going to feel really stupid when she switches doors and ends up with the goat. However, that'll only happen 1 out of every 3 tries. And importantly, if she initially picks a door that has a goat behind it, which will happen 2 out of every 3 times, because the host will be opening the other goat door, her decision to change doors will always result in a new car. What I'm saying is Carla's strategy of changing will win a new car 2 out of every 3 times. So since she's got 30 tries at this game show, we'd expect her to win 2/3 times 30 or 20 cars. Carla's strategy of changing doors wins a new car twice as often as Sarah's strategy of staying with her initial door. So changing doors is the better strategy and the answer to the Monty Hall problem. It's worth pointing out that implied in this analysis is that the host will always open a goat door and give us a chance to switch doors, regardless of whether we, the contestant, are in front of a goat door or the car door. However, if this weren't the case, our probabilities would change. For example, if the host was being a jerk and only offered us the option to change doors when we were standing in front of the car door, well then clearly we'd never want to change doors. And similarly, if the host was being super nice and only offered us the option to change doors when we were standing in front of the goat door, well then we'd always want to change doors. And while those two situations are fairly obvious, you can mess with the host's motivations to make some more interesting problems. In each of the following three scenarios, see if you can figure out whether A, the contestant should change doors, B, the contestant should stay in front of the door that they're standing in front of, or C, the probability of winning the car is the same whether they stay or change. I'll put the answers at the end of the video. In variant 1, you somehow know that the host has no idea where the car is. You select a door at random, the host opens one of the remaining two doors at random, and happens to reveal a goat. Should you stay, change, or does it not matter? In variant 2, the host picks a goat ahead of time that he will reveal as long as you're not standing in front of that door. If you are standing in front of that door, he doesn't even give you the option to change. So if you know this and he does give you the option to change, should you stay, change, or does it not matter? And finally, variant 3, which is similar to the original case, where the host will always open a goat door and give you the option to change. But you happen to know that if the host has the option of two goat doors to open, he's twice as likely to pick the goat door on the left than the goat door on the right. You want to stay, change, or does it not matter? All right, one more paradox I want to walk you through before telling you the answers to those previous questions and leaving you with the challenge question. This paradox is totally different from the Monty Hall question. It's definitely not the exact same question, just using different characters. So the way it goes is you got these three prisoners, Aaron, Brian, and Cletus. And sadly, all three are sentenced to death. However, the governor, just on a whim, decides he's going to pardon one of these three. So he chooses one totally at random and tells the warden. Aaron, one of the prisoners, gets word that one of the three of them is going to be pardoned. He begs the warden to tell him who it is, but the warden won't tell him. Instead, the warden tells him that it's definitely not Brian that's going to be pardoned. Aaron smiles a little smile, thinking that if Brian's not going to be pardoned, it's either him or Cletus. So his odds of getting pardoned just went up from 1/3 to 1/2. My question to you is he right? Are Aaron's odds of being pardoned now 1 in 2 instead of 1 in 3? If you're really clever, you might see some parallels between this and the Monty Hall problem. In fact, I lied to you. This is identical to the Monty Hall problem. I'm just sort of changing the story and changing some of the characters. Much like the Monty Hall problem where we had to be really careful with the motivations of the host, here we have to be really careful with the motivations of the warden. So assume that the warden was always going to tell Aaron the name of one of the other two prisoners who was not going to be pardoned. So think about it like this. Just like initially there's a 1/3 chance that the car is behind any of the three doors, initially there's a 1/3 chance for each of the prisoners to be pardoned. Our contestant picks the Aaron door, at which point the host opens the Brian door and reveals that he is not being pardoned. In the Monty Hall problem, we know that at this point, the contestant should definitely switch doors, as the door she's in front of only has a 1 in 3 chance of containing the car, but the other door has a 2 in 3 chance of containing the car. Similarly, if you were betting on one of the prisoners to be pardoned, you'd no longer want to bet on Aaron, and instead you'd want to bet on Cletus, because the reveal of Brian's pardon, informally speaking, transferred the 1/3 probability from Brian to Cletus. So the probability that Aaron gets pardoned is unchanged. It's still 1/3. Basically, the pardon is analogous to the new car. Aaron finding out about the pardon is analogous to us choosing that door to begin with. The warden revealing one of the remaining prisoners who will not be pardoned is analogous to the host opening a door and revealing a goat. The three prisoner paradox is fundamentally the same as the Monty Hall problem, just with different characters. As promised, here are the answers to the 3 questions from earlier in the video. And when you're ready, here's the challenge question for this week. This question really is fundamentally different from the Monty Hall problem, but it's another paradox that Marilyn wrote about in her column, so I thought I'd include it. As a minor hint, the answers to the 2 questions you see on the screen right now are not the same. If you want to share any thoughts, questions, or solutions, I'll look for them in the comments section.